Entropy changes in reversible processes. Entropy changes in reversible processes. For reversible processes, the entropy of the system may increase, decrease, or remain unchanged. The entropy change for the environment of the system will always be equal in magnitude but opposite in sign. Thus, in a reversible process, the entropy of the system plus environment remains constant. Change in entropy of the system can be calculated delta S equals S final minus S initial equal to dq over T integration from I initial state to final state. Entropy changes in irreversible processes. Since entropy is a state property, the difference in entropy between state I and F must depend only on those states and not at all on the way the system went from one state to the other. Suppose then that we replace the irreversible process with a reversible processes that connects the same state I and F. Now, this is irreversible process, have initial state and final state. We cannot plot the state between because it's not in equilibrium, okay? Define entropy change for an irreversible process occurring in closed system. Replace that process with any reversible process that connects the same initial and final states. This is the reverse process. This is reverse process. Initial state and final state are the same as this one. Calculate the entropy change for this reversible process with equation delta S equals S final minus Si equals integration dq over T from initial state to final state. We can find the entropy change in this reversible process, and actually it is equal to the entropy change of this irreversible processes. Let's look at the change in entropy in the irreversible process of the free expansion of an ideal gas. This is the figure. This figure A shows the gas in its initial equilibrium state I, confined by closed stop clock. The gas are confined to the left half path and in thermal isolated container. If we open the stop cock, the gas rush in to fill the entire container. Okay, eventually reach the final equilibrium state F. This is an irreversible process. All the molecules of the gas will never return by themselves to the left half of the container. Free expansion. We know free expansion, the Q is zero because isolate. The work is zero. Why? Because when you rush into this half, this is a vacuum, no resistance, no work has been done. According to the first law of thermodynamics, delta E equal to zero. And then we know delta E equals NCV delta T. Okay, so that means delta T equals zero. That means for free expansion, the initial state temperature and the final state temperature, they are the same. Okay? So, this reminds us, maybe we can find some isothermal reversible process, which can have the same initial state at this one and the same final state, this one. And if we calculate the entropy change for this isothermal reversible process, and actually it's equal to this entropy change for this free expansion. This shows how to produce a reversible isothermal expansion. Okay, we make the process reversible. It is done slowly in a series of small steps, with gas in an equilibrium state at the end of each step. Look, this one, this original state, we take the lead shot off, so the pressure goes down and the volume goes up, and we have a heat exchange here. Finally, this is the final state of the free expansion. Okay. We confine the gas to an isolated cylinder that rests on the thermal reservoir. Maintained at a temperature T. We begin by placing just enough lead shot on the mobile pistol, this is mobile pistol, so that the pressure and the volume of the gas are those of an initial state I for the figure 8. This figure 8 is previous figure 8. Okay. We then remove shot slowly, piece by piece, until the pressure and the volume of the gas are those of the final state F of the figure B. The temperature of the gas does not change because the gas remains in thermal contact with the reservoir throughout the process. The reversible isothermal expansion of the figure is physically quite different from the irreversible free expansion. However, both processes have the same initial state and the same final state, and thus must have the same change in entropy. Because we remove the lead shot slowly, the intermediate state of the gas are equilibrium states, so we can plot them in a PV diagram. Now, let us go back to free expansion. Okay, we know Q equals W equals 0, delta E equal to 0. So delta T equal to 0. T does not change. Okay, then we use an isothermal process to calculate the entropy change. Okay, this isothermal process, we can use this one to calculate. This is the temperature constant. So we can take this out. Okay, when you take it out, it's integration, differentiation. This is a Q. So equal to Q over T. Okay, if we can calculate this is the Q, Q equal to W. Okay, it is T. When the temperature change delta T of a system is small relative to the temperature before and after the process, the entropy change can be approximately S equal to this one. As this T is changed very small, we replace with the T average and take it out. And inside, we get an integration, differentiation, you get a Q. Okay, where T average is the average temperature of the system during the process. Example: 1 mole of nitrogen gas is confined to the left side of the container of the figure 8. And you open the stopcock, and the volume of the gas doubles. The gas rushes into another half. Okay. What is the entropy change of the gas for this irreversible process? Treat the gas as ideal. We try to use the isothermal process with the same temperature T as the irreversible process. Okay. And we calculate delta E. Delta E in turn equal to Q minus T, W equal to 0 because delta T is 0. And the Q equal to W. And the isothermal process work is calculated by nRT log V final over V initial. So, and ds, delta S equal to integration dq over t from initial state to final state. Since t is constant, we take out of the integration. Okay, we do the integration, you get a q. This is a q over t, and q is this one. So we put the q inside, the t cancel out. So delta S equal to nr log V final over V initial. In our case, V final doubled the initial, so this is 2. So this becomes nr log 2. This is the answer. This is the entropy change for isothermal processes. And this is also the entropy change for that irreversible process. This is also the entropy change for the free expansion. Sample. Figure A shows two identical couple blocks of mass m 1.5 kilogram. Block L is a temperature TIL 60 degrees Celsius, and the block R is a temperature TIR 20 degrees Celsius. The blocks are in thermal isolated box, okay, and are separated by an insulated shutter. When we lift the shutter, okay, these blocks eventually come to equilibrium temperature. T final equals 40 degrees Celsius. What is the net entropy change of the two block system during this irreversible process? The specific heat of copper is 386 joule per Kelvin per kilogram. Now, we use the two isothermal reversible process to replace this irreversible process. On the left, we see we have a reservoir contact with blocks, and we can change the temperature gradually. Okay, so in this case, it's starting from 60, and then finally it's 40. So delta S left equal to dq over t from integration from I state to final state. T is not constant, okay, from 60 to 40 degrees Celsius. Okay. And dq, we know this dq is conducting, so you could mc delta t dt. Okay, we do the integration. Okay, mc is constant from I to say you take it out. I to final. And this integration is log t. So the final we get is mc log t final over t initial. We put number. M is 1.5 kilogram. C is 386 per kilogram per Kelvin joule. And this temperature, we have to use the Kelvin. This is final is 40 plus 230 C. Initial is 60. So this is a minus number, minus 35.86 joule per Kelvin. Anyway, the same thing we calculate the delta S right, okay? Exactly the same thing, except the number different, okay? Should be MC log T final to T final. Here, T final is this one. T initial is 20 plus this one, okay? So get 38.6. And the total entropy change is the sum of these two, okay? Okay, we get about a 2.4 joule per Kelvin, okay? So this is the entropy change for these two reversible processes. And it's also equal to the entropy change of irreversible change, okay? Same thing.